Okay, I think it's about time for us to get started. Now, some of you may have seen an email. I know spring break is coming up, and we have a test scheduled for next Friday. Some of you may not want to be here next Friday, and that's a very understandable thing. And so I'm going to try to schedule a time, either Wednesday night or Thursday night, if you want to take the test early. I was toying with the idea of having the test after spring break, but I thought, nah, you guys have been planning this the whole semester. Surely you want to just get it done with, and not have it hanging over your head all of spring break. So that's what I'm assuming anyways. So some people have been wondering about the midterm. In particular, you have questions about how things were graded. And if you have questions about how things were graded, first thing I encourage you to do is to look at the solutions. They have been posted as of this morning. Go to our class website, go to the exams link, and if you look there, you will find the exam and the solutions. Now, the problems were out of 7 points, and on each problem, they were looking for certain specific things. So you might have a really good sense of what you're doing, but you made mistakes, and when you make mistakes, you get penalized, and small penalties add up. We're happy to look at things, and when I say we, that means me. Your TAs will have you come talk to me. But just keep in mind, you're not guaranteed that your grade will change. But if you are concerned, you should feel free to talk to me. Okay, so there's that. Any questions before we begin? All right. Well, let's see. So where are we? So we're starting new material, a new chapter of our lives, if you will. And last time we talked about sequences. So what's a sequence? Well, you can think of a sequence as a very long list of numbers. So you start somewhere, maybe you start at 0, A0, A1, A2, so forth and so on. You don't have to start at 0. The book likes to start at 1. You could start at 5 or 100. It doesn't really matter. Most of the questions that we're interested in, the beginning doesn't really make that much of a difference. What we're interested in is what happens towards the end. This little dot, dot, dot. That's what really matters, is that one part right there. Now this end dot, 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 whenever you see dot, dot, dot in mathematics, it's basically shorthand for and so on and so on. Or the pattern continues. Well, of course, when you see a dot, dot, dot on the end, it really means and so on forever. The pattern continues forever. Well, the problem is it's hard to do things forever. And we have to understand, what does that mean? Well, so for example, in the long run, what are you doing? Does A sub n do something? Does it approach a value? And so to answer that type of questions, we have this notion of limits. So we say that as n goes to infinity, A sub n is L. So in other words, this sequence of numbers is approaching L. If and only if, for any epsilon, there's some capital N. So that if n is bigger than capital N, A sub n minus L is less than epsilon. Now the way you should think about this is to say, look, we want to get close. That's what this A sub n minus L less than epsilon here is. But not only do we want to get close, we also want to stay close, which is why we say, look, for all n bigger than capital N. So eventually we get close, and then we stay close. So it's not enough just to say, oh, look, I'm nearby infinitely often. No. I'm nearby infinitely often and from some point onwards. And so that's what we mean when we say A sub n approaches L. Now limits behave very nicely. So for example, we have some basic rules. More or less, what you think should be true is often true. If A sub n has a limit, B sub n has a limit, say A and B respectively, then the sum goes to their sum. So the limit of A n plus B n is capital A plus capital B. The product A sub n times B n goes to the product A times B. If B is not 0, A sub n over B sub n goes to A over B. We also have squeeze. So we'll take a look at at this type of thing. This is a nice, useful way to bound behavior. A sub n is less than or equal to b sub n, less than or equal to c sub n. So in other words, we have these two sequences which probably are ones that we understand. We say, look, I know what's going on with these. I can control them. And then we have this one that's caught in the middle. So if a sub n and c sub n are nice in that they converge, then that means that also b sub n must converge to the same thing. One other thing we should note is that a lot of times when we come up with sequences, that we can think of them as being functions of some nice, sampling, some nice continuous function. So a sub n is f, a function evaluated at n. And that function, if it's a nice function, we can say, oh, look, we know how to work with nice functions. Well, what's nice? Nice means differentiable. And we can use tools. So, for instance, we can use L'Hopital. Now, there's some other things we mentioned last time. We talked about recursive definitions, and there's some other things that we didn't get to last time. So let's do one of those things we didn't get to. Now, this is not critical for what we're going to talk about, but it's a nice fact. And if you become a math major, or perhaps a math minor, this will be a nice thing to know. So we have the following. We say that a sequence, a sub n, and just as a reminder, when you see this notation, when you have braces, and you have almost like what's like you have for the evaluation, n equals k to infinity, just means we have this infinitely long sequence starting at a sub k. It's said to be monotonically increasing if the following behavior is true. A sub k is less than or equal to a sub k plus 1, less than or equal to ak plus 2, less than or equal to so forth and so on. So in other words, I can only go up. That's what it means to be monotonically increasing. Monotonically decreasing, well, it's similar, but now I can only go down. So a sub k is bigger than or equal to ak plus 1, it's bigger than or equal to ak plus 2, and so forth and so on. So whenever we see the word monotonic, it's either going up or going down. Now you might wonder, well, what does monotonic mean? Well, mono, that's one. And a tonic, it's a type of bitter drink often mixed with alcohol. So monotonic means you need at least one drink to believe it. So, all right, that's monotonic. Now, what's the fact? If you have a sequence which is monotonically increasing and it's bounded from above, it must converge. Must converge. And so this is a nice way to say, well, how do I know if something converges? We can say, well, it's always going up, and it can't keep going up forever. There's an upper bound. And that's enough. That's enough. Similarly, if it's monotonically decreasing. Okay, so here's an example. This one is one which is a recursive definition. So suppose you know a0 is 1. And that a sub n, what do? You take the square root of a sub n minus 1, add 2. Okay, well, so what does that say? Well, so a0 is 1. a1, that's the square root of 1 plus 2. Well, I can do that. That's 3. a2, that's the square root of 3 plus 2, which is square root of 3 plus 2. Can't really simplify that much. a3, well, that's the square root of 3 plus 2 plus 2. Okay, well, and you can imagine it's going to get more and more complicated as we go along. So the question is, well, does it converge? And if it converges, what does it converge to? Well, let's think about what we know. Suppose that a sub n is less than or equal to 4. For just a moment, let's just suppose that. Then let's look at a n plus 1, the next term. Well, that's the square root of a sub n plus 2. That's not very surprising. But what can I say about the square root of a sub n? If a sub n is less than or equal to 4, the square root of a sub n is less than or equal to 2. So that's also less than or equal to 4. So what is this saying? It says if I start off below 4 and I do one step, I stay below 4. So what this allows us to say is this says, look, a sub n is less than or equal to 4 for all n, as long as our first term is less than or equal to 4. Well, it just so happens that our first term was 1. So, good. 1 is less than or equal to 4. So what have I proven? I've proven it's bounded. It's bounded. Well, what else do I need to prove? Well, I have to prove monotonic. Is it monotonic? Well, let's think about what this is doing. If I'm thinking of this as a function, say a function of a sub n minus 1, what does that say about my function f of x? What function is it? So f of a sub n minus 1 is the square root of a sub n minus 1 plus 2. That says f of x would need to be what? It would have to be the square root of x plus 2. So in other words, I can look at my recurrence and I can figure out, well, what's the recursive function that I'm using here? Now, this is a little bit subtle, not too much though. What do we know about the function square root of x plus 2? Well, we know it looks like this. Now, question, is this function increasing? Yes. You see, what does that say? If the function is increasing, that tells me that I can use that fact to show that the iterate increases. And in particular, well, I won't go into too much detail. So the answer to is it monotonic? The answer is yes, and I won't be too rigorous on that. Now, it does converge. Can we figure out what it converges to? Well, let's think about it. Suppose it did converge, what would have to be true? Well, that would say that in the long run, a sub n is the limit. So for n very, very large, a sub n is essentially L. So if it did converge, and it has to because it's monotonic and it's increasing, I would have to have that L would be equal to, what can I say about this a sub n minus 1? What is it getting close to? It's also getting close to L. So it's getting close to the square root of L plus 2. Do we know a number with this amazing property that the number is equal to the square root of itself plus 2? 4. So it turns out that the limit is 4. Now, geometrically, we can see this. Here's a beautiful picture. I love this picture. And I'm going to take the function square root of x plus 2. Here's the function x. And if you watch the behavior, here's what happens. Initially, we start off at 1. So, I don't know, let's say this is at 1 here. So here's 1. Then, to get my next value, I plug into the function and I go over. There's my next value. Then I plug in and I go over. And what's happening is I'm climbing this staircase. So that here's 1, here's 3, here's that next number, square root of 3 plus 2, and so forth and so on. So I'm climbing up this staircase. It's this iterative process. And you can see that you say, well, look, if I do this stuff, I'm heading towards that intersection. So where this line, y equals x, intersects the line, square root of x plus 2. That's that computation. Y equals x equals square root of x plus 2. And so it does converge. Okay. All right, so let me put this up. I said it before, but it's an important idea. So I'll say it again. Perhaps if I say it many times, it'll sink in. When we talk about convergence, don't get distracted by what happens early on. What happens at the start can be highly, highly misleading. You don't need to look at the first 100,000 million terms. When we need to talk about convergence, you always ask, what happens in the long run? What's happening in that ... That's where convergence happens. It always happens at the tail, the end. That's where you need to focus your energy. Okay, so now, with that out of the way, we're ready to start today's topic. So last time, we talked about sequences. Today, we're going to talk about something a little different. We're going to talk about a series. A series of hopefully fortunate events. So what is a series? A series is the sum of a sequence. So you have the sequence of numbers, A0, A1, A2, and so forth and so on, AN, so forth and so on. And now I want to add them up. Okay, well, adding up numbers, that's not hard. And indeed, adding up for a while, it's not hard. Where does it get hard? Well, no surprise. The hard part is right at the end. That ... That's the hard part. Why is it hard? Well, there's a small problem. You see, it's impossible to actually add infinitely many things in a finite amount of time. So in other words, you say, well, start with your calculator, add 1, then you add a half, then you add a fourth, so forth and so on. You can say, well, keep going. Well, when are you going to stop? Well, keep going forever. Well, no. We've only got 2 hours for the final. We can't keep going forever. We can't. Oh, come on. You gotta make it easier on us. Okay. So look, we can't actually add them up, but we don't have to add them up. What do we need to do? Well, what we need to do is we have to say, what should happen? What should it be when I'm adding up these infinitely many things? Now, when you hear the phrase, what should it be, what do you think of? You think of limits. Limits answer the question, what should it be? And that's how we do sums. Okay, so when we talk about series, we say the following. What we do is we form what are called the partial sums. So the sums of the first few terms. And so we say, well, let's just sum of just the first number, A0. Okay, sum of the first two, A0 plus A1. Then A0 plus A1 plus A2. And so forth and so on. And we say, okay, what we're forming now is we have this sequence of numbers. So I'm trying to find an infinite sum. I say, well, look, instead of focusing on this infinite sum, I'm going to form an infinite sequence. It's the sequence of partial sums. So now I have this sequence of these S's. S0, S1, S2, S3, so forth and so on. And so now we say, well, look, if I want to know what should happen, I look at what's happening to these numbers, these Sn, these partial sums. And if these partial sums converge, then that's what we say, okay, that's what the sum should be. The infinite sum is going to be that limit of that sequence. All right, so that's our plan. So to add infinitely many things, we say, well, what should happen if we were to add infinitely many things? And then we say, that's what we will say happens. That's what we'll actually say happens. All right, so is our strategy clear? Look at partial sums, look for a pattern, say, aha, this is what happens. Okay, well, let's try one. All right, here's a nice sum. This will be a nice warm-up for us. 1 over 2 to the nth power. All right, well, what does that mean? Well, what this means here is I'm taking 1 over 2 to the 0, which is 1, plus a half, plus a fourth plus an eighth. And so I'm taking 1 over the powers of 2. And I'm trying to say, what happens if I were to add all of these things up? What would I get? Okay, so what's our plan? Well, we start by looking at the partial sums. So the partial sum, when I just add up the first term, which is 0, well, that's 1. All right. Next partial sum, 1 plus a half. Okay. All right. 1 plus a half. All right. Okay. I can believe that. Next partial sum, 1 plus a half plus a fourth. Well, maybe I should draw this. 3 halves. Okay, 1 plus a half plus a fourth. What does that become? So what? Well, it would be 3 halves plus 1/4. 3 halves plus a fourth, that's 6/4 plus 1/4, which is 7/4. Now, if you want, I can draw a picture here. Here's 0. Didn't add anything. Then we got to 1. Then we got to 3 halves. And then we got 7/4. What's next? 1 plus a half plus a fourth plus an eighth. Sorry, what? 15/16 would be over here. 15/8. Okay, that seems more reasonable. Okay, so 15 over 8. Okay, about here. Okay, well, Now, you look at these numbers, and numbers don't quite seem to make sense unless we say, perhaps there's a different way to view these numbers. Well, what's a different way to view these numbers? 1 happens to be 2 minus 1. It's a bold claim, but I think you'll agree with that one. How about 3 halves? What's another way to see that? 2 minus a half. 7/4? 2 minus a fourth. 15/8? 2 minus an eighth. See, what's happening is that there's this number here, 2. And you can imagine that what's happening? Well, I'm at 0. I want to get halfway to 2. Well, how much do I need to add? I need to have half of 2, which is 1. Okay, now, how much distance is left? 1. Well, now I want to get halfway again. Well, what's halfway? Well, I need to go half. So now I'll go to half. So went 1 plus a half. Okay, now what? Well, I'm at 3 halves. I want to get halfway to 2. Well, I'm a distance of half. I need half of that is a fourth. 1 plus a half plus a fourth. And so forth and so on. I think there's a question.
Is there a reason you chose to specifically, other than it's what it is converted to?
Well, I know ahead of time what's going to happen. And lots of practice. If we had kept going, I would say, so here's a good rule of thumb. If you don't know what to do, run it for a little bit and say, what are these numbers getting close to? You say, well, 15 over 8, what is that close to? Yes, there is an amazing efficient method on my next slide. But come on, that's the next slide. We got to work on this slide. You know, it's the slides of our lives, one day at a time. As the slides turn. I'm a little bit behind on my soap operas. What? Any others? All right. Anyways, but yes, there's an amazingly efficient method. So what's happening here? Well, what's happening is there's a different way to think of this process. It says, look, at every stage, you're trying to get halfway from where you currently are to 2. And so, of course, there's a joke about, I don't know if I'm allowed to tell jokes like this. Do it? Well, okay, if nobody laughs, I'll delete the recording. All right. So, there was a mathematician and an engineer, and they went out to a bar one night, and they said, well, here's sort of there's a really attractive person over there. I said, okay, but you can only go halfway between where you are now and where that person is. Okay, and then you can only go halfway again, and you can only go halfway again. And the mathematician thought, well, if I go halfway, I'm not there. If I go halfway again, I'm not there. If I go halfway again, still not there. I'll never get to that person. Okay, forget it. I'm not going to do it. Engineer thought, you know what? For all practical intents and purposes, after a few steps, I'm close enough. I'll do it. So, there's that philosophy. It's like, well, look, run it for a while and go. And if you look, and you can often tell, if you don't know what's happening, run it and see, okay, after 5, 10, it's roughly having this type of behavior, and that's a good guess, and it helps drive a guess. Now, it turns out, and instead of spending a lot of time proving it, because the next slide does it so much better, it turns out that what's true is that if I look at the nth partial sum, it's 2 minus 1 over 2 to the nth power. So essentially, I'm halving my distance at every stage, and halving it from where I am from 2. All right, so given that you believe that, and it's okay if you don't, we will prove it in just a moment. But suppose you do believe that, then what is true about this sum? This infinite sum, what would it do? Converges to 2. So we would say that the infinite sum is 2, because the partial sums converge to 2. Now, what you're seeing here, this is a very special type of sum. Now, instead of thinking of it as 1 over 2 to the n, there's an alternative way to think of it. That's sum n equals 0 to infinity of the following, namely 1/2 to the nth power. So 1 over 2 to the n is the same as 1/2 to the nth power. And, all right, so what kind of series is that? Well, the answer is, it's what's known as a geometric series. So here we go. So a geometric series has the following basic form. You start, it's a summation from 0 to infinity, a times r to the k power. K is our index. Now, in case you're wondering, is there something special about k that I chose? The answer is no. No, there's nothing special about k. I could have chosen any letter of the alphabet or any emoji or anything. Just k is sort of traditional. It's tradition. Okay, so what does it look like? Well, it's a plus a times r plus a times r squared, a times r cubed, a times r to the 4th, and so forth and so on. Now you might say, why are we calling this geometric? So in mathematics, you'll hear oftentimes two things referred to, arithmetic and geometric. Arithmetic refers to addition. Geometric refers to multiplication. So when you hear somebody talk about the geometric mean, that just means there's something dealing with multiplication. So here, the reason why we call it a geometric series is because we're multiplying at every stage by r. We're adding an extra factor of r. It's that multiplication. That's why you're calling it geometric. Okay, so how do we sum a geometric series? Well, I want to compute the nth partial sum, and I want to do it in a smart way. So we'll do the following. We'll say, well, what is the nth partial sum? Well, it's a plus a times r plus a times r squared, so forth and so on, up to a times r to the n. It's the sum up through the nth term. Now, that's not so surprising. Now what I'm going to do is I'm going to take that sum, and I'm going to multiply it by r. What happens? Well, what happens is a times r becomes ar. 8r times r becomes ar squared. Ar squared will become ar cubed, and so forth and so on, up to the n. Ar to the n minus 2 multiplied by r becomes ar to the n minus 1. Ar to the n minus 1 times r becomes ar to the n, and ar to the n becomes ar to the n plus 1. So by multiplying by r, I'm essentially shifting everything over. Now we subtract. Sn minus r times Sn. Well, you'll see that there's nothing canceling below the a, so I get a, then I get cancellation, cancellation, cancel. Almost everything cancels. So the beautiful thing is that all that middle stuff disappears. The thing that doesn't cancel is the very end. So I'll get minus arn plus 1. And therefore, Sn, this partial sum, assuming that r is not 1, because if r is 1, this is a really bad thing that we just did. But let's just assume r is not 1. Then what we get is that it's a minus a r to the n plus 1 power over 1 minus r. So in other words, partial sums of geometric series are easy. Very nice. Very nice. Now, you might remember something we talked about last time. We said the following. If r is small, and small for us meant smaller than 1 in absolute value, so in other words, between negative 1 and positive 1. If r is small, and I raise that to a large power, what's happening is it shrinks, it shrinks, it shrinks, it shrinks, it shrinks. It goes to 0, as then goes to infinity. Now, why do I point this out? Well, the reason I point this out is that the only place that n is showing up is in that exponent there, r to the n plus 1. Everything else, the a and the 1 minus r, is fixed. A is fixed, 1 minus r is fixed, and that goes to 0. And therefore, the partial sums, assuming that r is small, converge to a over 1 minus r. And so you have the following very beautiful basic fact. If r is less than 1 in absolute value, then the summation from 0 to infinity of a times r to the k is a over 1 minus r. You'll notice there's a box. The box indicates this is important. And geometric series are amazingly important. We are going to come back to them time and time again. So you should know this formula. It is going to be an important formula to know. As an example, now the problem we just did is very straightforward. Sum k equals 0 to infinity of 1/2 to the k power. Well, what is that? Well, a is 1, so it's 1 over 1 minus r. R is 1/2. 1 minus 1/2 is 1/2. Then I'm flipping it, so it becomes 2. So once you have that framework, geometric series, very quick, very quick. Okay, let's try an example. Try to see if we can keep that on the same screen. Suppose we want to find the following. The summation from 0 to infinity of negative 2 to the k over 5 to the k. Well, what do? Yeah, so this is the same thing as the summation k equals 0 to infinity of negative 2/5 to the kth power. So what kind of series do we have? It's geometric. All right. What is A? A is 1. What is R? Negative 2/5. Now, is it okay that R is negative? Yes, it's okay. Is it between negative 1 and 1? Yes. If it's not between negative 1 and 1, we're in trouble. But we're okay. So we apply the formula. This would be 1 over 1 minus 2/5. Or, if you like, this is 1 over 1 plus 2/5. 1 plus 2/5, also known as 7/5. 1 over 7/5, but we can make that look nicer. That is 5/7. And there we go. All right. Well, that's not so bad. That's not so bad. We should hope for one of those on the test next week. All right. Let's try one maybe a little bit more interesting, not too much more interesting. We'll work our way up to it. So here's another one. Find the summation from 2 to infinity of 3k plus 2 over 4 to the k. Well, what can we do? What do we do? What are some differences? Now, hopefully, you'll notice there's an important difference in where we start. This assumes our formula that we start at 0. But here we're starting at 2. What do we do? There's perhaps a suggestion.
Isn't that 3 squared 9?
Well, 3 squared is 9. So we certainly what we can do is we can break up the 3k plus 2. We can write this as sum k equals 2 to infinity as 3 to the k times 9 over 4 to the k. That we can do.
Where did the
3 squared. The plus 2 is in the exponent. I know, you're probably thinking, oh, his handwriting is terrible. How do they let him out? Yeah, that's my poor handwriting. I apologize. Yes? Okay, so we can certainly do that. So this is the sum, k equals 2 to infinity, of 3/4 to the k times 9. That's certainly true. Now, I'm making you nervous. You're like, okay, there must be something tricky here. Otherwise, he wouldn't hesitate so much. I'm not trying to make you nervous. I'm probably succeeding, though. Sorry, what? Well, okay, so there's a couple of things we can do. Now, one thing we can do is, if in doubt, let's just write out what's happening. This is 9 times 3/4 squared plus 9 times 3/4 cubed plus 9 times 3/4 to the 4th, and so on and so forth. So if you're not really sure what's happening, write out the first couple of terms. And so you'll notice here, one thing you can do is you can, they're more or less the same philosophy, anything you talk about. But you can say, well, what really does a geometric series look like? So if I go back to what a geometric series really looks like, it says, I have some term, A, that's my first term, and then every term I'm multiplying by some R. So my first term is 9 times 3/4 squared. But then, to get my second term, what do? What did I do to get from the first to the second? I multiplied by 3 over 4. What did I do to get from the next term to the next term? What am I doing? I'm multiplying by this 3 over 4. So one way I can think of this, and this is, I like to think of this way. I'm an old person, so I have to do math slowly. 9 times 3/4 squared, I just pull that out. And if I pull that out, the first term would be 1 plus 3/4 to the 1 plus 3/4 squared plus 3/4 cubed, and so forth and so on. And this term right here, that's much more easy for me to digest. I can write this in a nice way. This is the same as the sum, k equals 0 to infinity of 3/4 to the k. Essentially what's happened here is we started with the sum from k equals 2 to infinity, and we rewrote the sum, changing our indexing. Now, this might not feel comfortable to you yet, and it might not ever feel comfortable to you, but we're going to do this a lot more, especially when we get towards the end of chapter 10. So the ability to say, well, here's one way to write my sum, but let me write it in a different way. I will say, in case you're wondering what we've done, a lot of what we do you can relate back to types of integration ideas. And, essentially what I've done is I said, let's take our k and shift it by 2. So k, let's see, I want to make sure I oftentimes, now I really am getting old. Okay, so k went to k minus 2 or k plus 2. I can never do this off the top of my head. Yeah. This will make more sense. I'll do it much better next time. Okay, let's finish this up. Okay, so what do I have? Well, this part, this is my a. So I have 9 times 3/4 squared. And what does this sum become? One over 1 minus 3/4. Well, 1 minus 3/4 is also known as 1/4. And I flip it. So what do I have? I have 9 times 9 over 16 times 4, because this 1/4 flips over to 4. And then I can cancel off a single 4, and I get as my final answer, this is 81/4. Okay. All right. Let's see. In the interest of time, we'll save that for next time. Here we go. So geometric series, very important. It's one of our basic things that we know how to add. There's another type of series that we like. We call these telescoping sums. And I think we like to call these telescoping sums because I'm reminded of if you've seen some pirate movies, like maybe Pirates of the Caribbean, and you see Captain Jack, and he pulls out his telescope, and he extends it, and then he can collapse it. So it's this idea of like you're taking something that's very long and collapses down to something very short. And so the idea is we say a sum is telescoping if you get cancellation. Lots of cancellation, things collapse, life is good. So the easiest way to see this is to do an example. The summation from n equals 1 to infinity of 1 over n times n plus 1. Now you're thinking, that sounds hard. And normally it would be. But let's think of it in a different way. Suppose you were still in your departmental midterm mode, and you had seen something that said 1 over n times n plus 1. What would you think to do? You would think partial fractions. Let's do it. Let's do it. Come on, we can do it. This is cool. Okay, so it's something over n plus something over n plus 1. Now you're probably thinking, really, partial fractions? Yeah, really, it's totally cool. It's awesome. Okay, so clear our denominators. We get 1 equals a times n plus 1 plus b times n. And really, you can think of n as any number you like. You can solve for coefficients, do whatever you want. In our case, well, let's just pick on some nice numbers. If I plug in n equals 0, what do I get? Well, I'll get 1 equals a. Well, that's easy. What's another nice number? -1. Plug in -1, what do I get? 1 equals -b. Okay, so that I can conclude that a over n plus b over n plus 1, that's really 1 over n minus 1 over n plus 1. Now, to understand the infinite sum, we look at the partial sum. So Sn, unfortunately, well, let's choose Sk, it doesn't really matter. The summation n equals 1 up to k of 1 over n times n plus 1. But this is really the summation n equals 1 to k of 1 over n minus 1 over n plus 1. What does that look like? It looks like the following. 1 over 1 minus 1 over 2. That's n equals 1. Plus 1 over 2 minus 1 over 3. That's n equals 2. Plus 1 over 3 minus 1 over 4. That's n equals 3. 1 over 4 minus 1 over 5. That's n equals 4. And you keep going till eventually you get to 1 over k minus 1 over k plus 1. All right. Now, looking at this, can anything simplify? The 1/2 can cancel. That's progress. Anything else? The 1/3 can cancel. The 1/4 can cancel. The 1/5 will cancel with what's next in the sequence, and that'll keep going, and then there's a 1 over k minus 1 over k and a plus 1 over k will cancel. What doesn't cancel? The first term, the last term. So that my partial sum looks like 1 minus 1 over k plus 1. Well, that's my partial sum. If I want to understand my sum, I ask, what happens as I let k go to infinity? So as k goes to infinity, Sk does what? Goes to 1. What does that mean about this sum? It goes to 1. Now, you're thinking, well, so were we allowed to do partial fractions? Yes. In fact, a lot of the ideas in calculus you'll see are expressed here again. Partial fractions we've talked about. Reindexing is really substitution, just shifting your sums. We'll do much better examples of that next time. Even the sums from n equals 1 to infinity, that's like improper integration, where we have to go and say, well, what's the limit? Take the limit as we go to infinity. And I'm guessing that you're really excited to head out, so maybe I guess we'll stop here. All right. See you next time.